So, have you ever just stopped and wondered what holds literally everything together? I mean, from the air you're breathing to the phone in your hand, it all comes down to the incredible energy locked inside chemical bonds. And in this explainer, we are going to dive deep and unpack that energy. Right? It's a fantastic question. And the answer, believe it or not, is basically a simple tug of war. You see, every single chemical reaction is about two things: breaking old bonds and forming new ones. And the secret to whether it's an explosion or an ice pack really just depends on if you get more energy out of the deal than you had to put in. Okay, so here is the single most important rule to remember. Think about it like you're making an investment. To break a bond, you have to put energy in. It costs you something, kind of like the effort it takes to snap a twig. But when new, more stable bonds form, you get this huge energy payout, usually in the form of heat. And that simple exchange, energy in versus energy out, governs all of chemistry. All right, let's jump into our first type of bond, covalent bonds. This is where atoms are all about sharing electrons. But, not all sharing is created equal. So, how do we actually measure how strong that connection is? Well, we measure this with something called bond dissociation energy. It sounds complicated, but really, it's just a number that tells us how much energy it takes to break a whole bunch of these bonds. 1 mole, to be exact. The higher the number, the tougher the bond is to break. For instance, it takes a whopping 436 kilojoules just to break apart the hydrogen-hydrogen bonds in only 2 grams of hydrogen gas. That's a lot of energy. Now, this is where it gets really cool. Check out the clear pattern here. As these carbon atoms share more and more electrons, going from a single to a double to a triple bond, look at what happens. The bond energy just skyrockets. And at the same time, the atoms get pulled in closer, making the bond not only way stronger, but also shorter. And here's where this becomes super useful. We can actually use these numbers to do a bit of, let's call it chemical accounting. By adding up the energy cost to break all the old bonds and then subtracting the energy payout from all the new bonds, we can get a pretty good estimate of the total energy change for a reaction. Scientists have a name for this: enthalpy change, or delta H. And the process is actually pretty straightforward. It's just 3 steps. First, you add up all the energy you need to break every single bond in your starting materials. That's your energy investment. Second, you add up all the energy you get back when the new bonds form in your products. That's your energy return. The difference between those two tells you if the reaction is going to release heat or get cold. So let's take a look. When you do the math for a reaction like hydrogen gas bumping into chlorine gas, you get this: -185. And that little minus sign? That is the key. It means way more energy was released making the new bonds than was spent breaking the old ones. That leftover 185 kilojoules gets released as heat, which is exactly why we call this an exothermic reaction. Okay, let's switch gears and talk about our second type: ionic bonds. If covalent bonds are like a friendly sharing agreement, ionic bonds are more like a powerful magnetic attraction between positive and negative charges. And let me tell you, this creates an even stronger connection. Now, with ionic compounds, we have to look at the bigger picture. We measure the strength of the entire crystal structure, and we call that lattice energy. To get a feel for this, imagine taking a solid crystal of salt and pumping in enough energy to rip every single positive and negative ion away from each other, turning the whole thing into a gas. The higher that lattice energy, the more stable and rock solid that compound is. So what makes that lattice so strong? Well, it really just boils down to 2 simple rules. First, bigger charges, like a +2 and a -2, create a much stronger attraction. And second, smaller ions can pack together more tightly, which also ramps up the force holding everything together. I mean, just look at the power of charge right here. On one hand, you've got lithium fluoride with +1 and -1 ions. On the other, magnesium oxide with +2 and -2. They're pretty similar in size, but just by doubling the charge on those ions, the lattice energy practically quadruples. It's a massive effect. Now, size matters too, even though charge is definitely the heavyweight champ. Here, we're comparing 2 magnesium compounds. The fluoride ion is tiny, while the iodide ion is much bigger. This lets that little fluoride ion snuggle in way closer to the magnesium, creating a tighter, stronger lattice and a much higher lattice energy for MgF2. So this raises a really good question. You can't exactly stick a thermometer into a crystal and measure the energy it takes to vaporize it into ions, right? So if we can't measure lattice energy directly, how on earth do we know these numbers? Well, the answer is a really clever energy puzzle. It's called the Born-Haber cycle. And the idea is genius. Chemists can measure the energy of every single little step it takes to form an ionic solid from its basic elements, except for that one final step where the crystal lattice actually snaps together. But since energy can't be created or destroyed, they can treat the whole thing like a math problem. By adding up all the known energy steps, they can solve for the one missing piece, the lattice energy. It's a brilliant workaround. So, after all that, what's the big takeaway here? Well, understanding why and how these bonds differ in strength explains so much about the world around us, from why salt is a hard crystal to where the energy in your breakfast comes from. So let's put it side by side. Covalent bond strength is measured between just two atoms, and it's typically in the hundreds of kilojoules. But ionic bond strength, that lattice energy, it accounts for all the attractions in an entire crystal, and that means their energies are usually much, much higher, often in the thousands. That's why ionic compounds like table salt have such insanely high melting point. When you get right down to it, the energy locked away in these chemical bonds is what drives our entire world. It's in the fuel in our cars, the food that keeps us alive, and the materials we build our cities with. It really makes you wonder, doesn't it? What is the absolute strongest chemical bond out there in the universe?